Hi students, hope everyone is fine and safe. It gives me immense pleasure to welcome you all to my new video, and today's video is about another interesting concept in the subject short range wireless communication. We're going to see frequency synthesizer and direct digital synthesizer. In previous video we have seen what is the working of RF transmitter, where we have seen the importance of frequency synthesizer and direct digital synthesizer. And today we are going to see the working of frequency synthesizer and DDS, which is direct digital synthesizers, right? And before starting with frequency synthesizer, we got to know why we need frequency synthesizer. What is the importance of frequency synthesizer? Frequency synthesizer is mostly used in RF transmitters, like it can generate an RF source. That is, the basic role of frequency synthesizer is to generate more than one frequency from one frequency element, right? Say for example, if you have one crystal oscillator, we can able to obtain one particular frequency, right? From that one single frequency component, we can able to obtain multiple frequency components, right? That is called as frequency synthesizing. And this frequency synthesizer, apart from this, this can be used for two other reasons. One is the output frequency is directly obtained from an oscillator without using multipliers, and similarly we can able to achieve higher deviation in frequency modulation than when directly modulating the crystal oscillator, right? So these are the main reasons we use a frequency synthesizer. And when it comes to working of frequency synthesizer, you can see this frequency synthesizer is PLL based frequency synthesizer. PLL based frequency synthesizer. This will work as the phase lock loop, right? And in order to understand this working of this frequency synthesizer, you ought to know the working of PLL, phase lock loop. What is PLL, right? So first we'll explain you what is PLL, and then we'll come back to this frequency synthesizer. So when it comes to PLL, PLL is normally used from computing to communication devices. It has wide range of applications in most of the electronic circuits, right? And predominantly in communication, it is used for achieving synchronization, and it is used for modulation and demodulation purposes in order to recover the clock signal, right? So these are the main applications of PLL, right? It is almost used in almost all the electronic devices, communication devices, right? And when it comes to working of it, first, in order to understand the PLL working, you have to know what is the working of voltage controlled oscillator, right? We know that oscillator is capable of generating signals, that is generating frequencies, right? So voltage controlled oscillator, it will generate signals at different frequencies, a particular frequency. We call that frequency as F0, right? So this voltage controlled oscillator, this oscillator can generate signal at the frequency of F0, which is free running frequency, right? And this particular oscillator, this frequency can be controlled by a controlled voltage, controlled signal. That controlled signal can be either a current or a voltage, right? Say for example, we have voltage. Now this, based upon this voltage, the input voltage which we give, then the corresponding signal will be generated. So this frequency, right, it is controlled by this particular voltage, and that is why it is called as voltage controlled oscillator. This voltage controlled oscillator is very important in PLL, right? So to understand the working of PLL, we'll just see the basic diagram of PLL. This is the basic PLL diagram, where you can see it has a phase detector, we have a low pass filter and voltage controlled oscillator. Now you understand what is voltage controlled oscillator. It will generate signals based upon the control signal, right? We can able to control the frequency of voltage control oscillator with this particular voltage, right? And now coming to PLL, what is the working of PLL is? PLL is mainly used for synchronization purpose. As I said, it can be used for clock recovery. That is, it can able to, it will take the reference signal, and we can able to lock the frequency of this reference signal. The output of this PLL will be in phase with this particular reference signal, right? It will be locked with this particular reference signal, right? So when we say the frequency is locked, right, with this output signal and the reference signal is locked, then the frequency and phase will be same. There will not be any phase difference, right? That is the working of PLL. And how we can able to achieve it? That is, we will have a reference signal. Reference signal is nothing but a crystal oscillator signal. Any crystal oscillator signal, any oscillator signal, that will be used as a reference signal. That will be given to the phase detector. This phase detector will generate an error signal. The signal which is obtained from the phase detector is called as error signal, and that error signal will be obtained from the feedback signal. That is, you can see here, the output of this VC0 is given as a feedback to this particular phase detector. So one input of the phase detector will be this reference signal, and the other input will be this feedback signal. And based upon the difference between these two signals, the phase difference between these two signals, error signal will be generated, right? And that error signal will be filtered, right? It will be filtered, and then it is that particular error signal will be given to the VC0, where that particular signal will be acting as a control signal to control the VC0, right? So now what will happen based upon this control signal? Now the VC0 will generate the output signal, right? And initially there will be a more error signal, because first there will not be any feedback, there will be a zero signal. Like once after the VC0 generated signal, that will be given as a feedback here. So the difference here between the reference signal and as well as this particular VC0 signal will be more, right? So the error will be more, and based upon that it will generate the VC0. So next time what will happen? The error will be reduced, right? And next time again the error will be reduced. Like that, the signal which is generated here, it will be becoming closer to this reference signal, and at one particular point these two signals will be equal, right? It will be equal, and PLL will achieve the locked condition at that particular stage. What is locked condition? So that the reference signal and the feedback signal will be locked, right? So there will not be any frequency deviations, right? And more or less there will be a same phase difference, right? That is, you will not have any phase difference, or you will have a constant phase difference, right? So that is called as lock stage. And there is something called capture stage, that is capture range. And you have to understand what is lock range, and you have to understand what is capture range. You understand what is lock stage. Lock stage is where both the reference signal and the output signal will be locked, that will be in the same frequency and same phase, right? And lock range is the range of frequencies over which this lock condition will be maintained, right? Where the input signal and the output signal will be same. Then that is called as lock range. And what is capture range? From name itself you can understand, capture range is the range where we will achieve that particular lock condition, right? That is, as I said, depending upon the iteration, right, the error signal get closer and closer, and it becomes locked, right? So the range at which the lock is obtained, that is called as capture range, right? So this is the basic working of PLL, right? And when I say there is no phase difference or constant phase difference, you have to understand what is no phase difference, what is constant phase difference. That is, if you take any particular signal, if you take this particular signal, if you take this signal, right, you can see this signal has same frequency, this signal has same frequency but different phase. And when in this signal you will have different phase here, but the phase difference is constant, because constantly it is varying, right? So the phase difference will be constant, even though the phase is different, the phase difference will be constant, right? And this is what I said, even though there is a phase difference, there will be a constant phase difference here, right? The phase difference will be constant, but the starting point here, there will be a phase shift here, right? Similarly, there will be other signal where you will have, you can see this particular signal. Just for an example, if you take this particular signal, if you see the signal, the phase is same, that is, both are starting at the same point, but the phase will vary constantly. You can see the phase is constantly varying depending upon the time, and the frequency is completely different. Whereas here, even though it starts at different position, the phase difference is constant, right? So when in the locked condition, the phase difference will be zero, right? So the input frequency and as well as the output signal frequency will be same, right? And now, what is frequency synthesizer? Why is that we are seeing the PLL here? Frequency synthesizer can be obtained using PLL. That is, another application of PLL is frequency synthesizer, right? That is, we can able to generate more frequency from one frequency signal, right? You can see here we have a phase detector, we have local oscillator, we have low pass filter and local oscillator. The concept is same here, right? So the signal which is coming out from here, right, it will be controlling the voltage controlled oscillator, right, and that signal is given as a feedback here, right? I'll come back to this, right? The same PLL, but we have now this PLL is used as a frequency synthesizer. How is that we can able to obtain frequency synthesizer? That is, if you're going to use frequency divider, right? That is, you can see here the output of this voltage control oscillator, right? The frequency obtained from this voltage control oscillator, if we divide that frequency, right? If we divide that frequency, we can able to obtain the multiples of the input frequency, multiples of this particular frequency, right? That is, whatever signal which is obtained, that will be divided, right? And that signal, from that signal it will generate the error signal, and the error signal will control the voltage control oscillator. Once again, the same process continues, but we can able to obtain the multiple versions of the input signal, multiples of input signal. That is, I'll give you an example here. Say for example, if you generate a crystal oscillator that is having 1 megahertz, right? And say for example, you have the voltage control oscillator that is also capable of generating 1 megahertz signal, right? The output of this VC0 is 1 megahertz signal, and once that 1 megahertz signal is given to this frequency divider, say for example, if this n is 10, then what will happen? Then this frequency m 1 megahertz will be divided by 10, and this signal, that is the second input to the phase detector, will be 100 kilohertz. Right? So now the phase detector, what it will do, right? Now it will take this 1 megahertz signal, one input, and the other input is 100 kilohertz signal, and then it generates the error voltage depending upon this difference, right? And we know that this particular signal, right, 1 megahertz has to be generated, right? That is, this error signal will be generated in such a way that next time the frequency divider output will be 1 megahertz, right? And if it has to generate 1 megahertz, then definitely the output has to be 10 megahertz, right? So that we can able to obtain the multiple of input frequency. You can see there 1 into 10, that is number of frequency divider. Whatever frequency divider we use, we can able to obtain the multiples of that particular frequency as the output, right? That is the working of frequency divider, right, where we call this as frequency synthesizer. From a single frequency component, we can able to synthesize many frequencies, right? And there is a working of prescaler. What is the working of prescaler? The prescaler here, once again, it will also do the same process. That is, normally prescaler is used to convert a high frequency electric signal into a low frequency signals, right, by using integrated circuit, right? But here we have used this prescaler so that we can able to increase this frequency, increase this incremental frequency of the frequency synthesizer. By using prescaler, we can able to increase the incremental frequency of frequency synthesizer. And similarly, right, we can also use reference divider. That is, if we use frequency divider, right, we can able to obtain multiples of input frequency, right? And whereas if we use reference divider, that is the original reference signal from the crystal oscillator, that will be divided by a factor of m, right? Say for example, if it is 8, right, then if you use reference divider here, then our output, right, that is the output generated by VFO, that is voltage control oscillator, can be divided by 8, right? So here we can able to obtain the divided version of the input signal, whereas with the frequency divider we can able to obtain the multiple version of the input signal, right? So this is the complete working of frequency synthesizer. And we have different versions of phase detector as well, right? That is, in analog modulator, that is, if you're going to use analog multiplier, this analog multiplier, there it works based upon the phase difference between these two signals. It depends upon the phase difference between these two signals. And there is the digital version of phase detector as well, where there will not be any phase difference. It will lock the signal, it will work, the log between the reference signal and the input signal will be zero. The phase difference will be zero. We will see that, the theory. But this is the working of frequency synthesizer. So whatever I said, that is explained here. You can see this is the basic component of reference crystal oscillator, that is phase frequency detector, low pass filter, voltage controlled oscillator, and we can able to control this oscillator frequency by using control voltage, and also we can able to achieve that by using varactor diode, right? And I have said what is error signal generated by the phase detector, that is proportional to the phase difference between these two signals, right? And the reference input that is obtained from the crystal oscillator, we can able to divide the signal so that we can able to obtain it from a frequency divider. Similarly, the low pass filter, that is determines the stability of PLL, the speed of response, and spurious output frequencies and noise. And similarly, you can see here the division ratio, that is I said about frequency divider circuit. Depending upon this, we can able to obtain the multiples of frequencies, right? So you can see here the divider ratio of main frequency divider determines the output frequency. Increasing or decreasing n by 1 increases or decreases the output frequency, right? Similarly, the prescaler will act as a low value high divider, whereas it will act as an incremental frequency for, that is, it will increases the incremental frequency of frequency synthesizer. And when it comes to phase detector, as I said, it can be of two types. One is analog multiplier, where it works based upon the phase difference between these two signals, right? You will have a phase difference, that is whenever the two signals are different frequency, then there will be a phase. That is, what is two signals? That is reference signal and the feedback signal. If these two signals are different frequencies, then there will be a phase difference, and based upon this phase difference, the control voltage will be generated. And when the control voltage is generated, it will control the VC0. This is the conventional analog multiplier, right? And when we use analog multiplier, definitely we need a frequency discriminator circuit, right? Because in order to bring the VC0 frequency to the lock range, we need a frequency discriminator, right? Whereas I have said that we can also use a digital version of phase detector, which is called as charge pump PLL, where it can be a digital device where we don't need this frequency discriminator, because it works based upon the sending voltages, that is the reference signal, and the feedback signal. Both the signals will be locked if there is zero phase difference. If there is zero phase difference, whereas in analog multiplier, it works based upon the phase difference between these two signals, right? So the charge pump PLL locks both the input signal to zero phase difference between them, right? So that we don't need frequency discriminator and phase detector, right? So that is the difference between the phase detector and as well as that is the analog multiplier and as well as the charge pump phase detector. And I already said what is capture range and lock range, right? Capture range is the range where the PLL will achieve the locked condition, right? And locked range is the range where the PLL maintains the locked condition between the input signal and the output signal, right? And this lock range can also be called as tracking range, right? And in order to understand what is this tracking range, what is going to be locked condition, say for example, as I said, like you have this particular frequency F, right? And you take this particular component, this is F, and you have the VC0 frequency like this, right? During the locked condition, during capture range, what will happen? It will move closer to this particular frequency F, right? And during locked condition, this signal will become single signal. That is, it will be in locked condition, so that even if there is a change in signal frequency, even if there is a change in input signal frequency, the reference signal frequency, then the feedback signal also will change according to the input signal. So in the locked condition, there will not be any frequency deviation. Even if this F moves further here, then the signal, the feedback signal also will be moving to that particular signal during the locked condition. And after the lock range, then there will be a frequency deviation between the input signal and the VC0 signal, right? So this is the complete working of frequency synthesizer. And now we will see what is direct digital synthesizing. Direct digital synthesizing is also a RF source, where here we can able to generate signal digitally, right? We can able to generate signal digitally. When we say digitally, we can able to achieve precise control over frequency, amplitude, and as well as phase, right? That is, by using software, we can able to generate the signal, we can able to determine, we can able to achieve the desired amplitude, frequency, and carrier whenever we need complicated waveforms, right? So it is like a digital device which can be used by a software, so that we can able to generate the RF signal based upon the requirement. Precise control of frequency, phase, and as well as amplitude can be achieved, right? So the direct digital synthesizers right now is not used for short range communications, but in future it can be used like as the devices are become very sophisticated. In future we will use DDS for short range communications. And DDS involves generating digitally, that is, instead of being used analog oscillator, we can use digitally, right? That is, a digital word can represent a sine wave, and that particular sample, that is, that particular digital word can be converted to an analog signal, and then it can be filtered, right? And the output of those frequencies can be in the tens of megahertz. And as I said, it can be used in it cannot be used in short range devices, but it can be used in PLL, UHF, microwave signals. And the amplitude, frequency, and phase modulation can be applied directly by using software, right? So that we can able to achieve greater flexibility whenever we need a complex or precise waveforms are required. That is direct digitally generating the carrier waveforms. That is called as direct digital synthesizers. So today what we have seen is, we have seen the working of frequency synthesizers and direct digital synthesizers, and we have seen the complete working of PLL, what is lock range, what is capture range, how the frequency divider is used, how prescaler is used. I believe this video will be very useful for you. Thank you, my dear students.